Hello everyone, I hope you all are doing well. This side Priya Bhatia, and in this particular video we will be talking about the optimization of KNN algorithm that we have covered up so far. First of all, in this video I will talk about that what is the literal meaning of optimization, followed by the two approaches that we have. One is KD tree and another one is ball tree. We will try to discuss the internals behind that. Just to make sure it will be good if you have a good idea about the binary search tree data structure with respect to this specific video, because somehow we are using that concept, although I'll try to explain you in a brief context that what is the meaning of BST, how basically or what are the rules and norms that we have as a part of a binary search tree data structure. But if you can do your own research prior to this, it would be of great help. So without wasting any time, let's get started. So whenever we are talking about optimization, right? Optimization simply indicates that we want to find that algorithm, or we want to, I would say, reframe that same KNN algorithm in a way that we will be able to reduce its time and space complexity. So I don't know how many of you are already aware about the concepts of data structure algorithms. That is where usually we try to understand this concept of optimization. But I'm giving you a brief overview that what is the meaning of this optimization word before we will jump towards it, how researchers will be able to optimize this KNN algorithm in a better manner. There we have two ways which they have found out. One is KD tree and another one is something called as a bold tree, right? Bold tree. So I will try to talk about both of them in a great detail today. But before moving towards that part, let me try to first of all focus on what is the meaning of optimization, because it's very, very important to understand that what is the literal meaning of that, okay? So whenever we're talking about optimization, it simply indicates that somehow I want to reduce the time complexity of a code, plus I want to reduce the space complexity of a given code. Space complexity of a given code. So we want to reduce both of them, right? Time as well as space. What is the meaning of time? That the execution time to required for the training and the testing per se to give us the final prediction is the time complexity. And how much extra space my algorithm is taking in order to do that particular task is the space complexity, right? So whenever we're talking about this KD tree, it somehow helps us to reduce the time complexity in a way that it focuses on the concept of binary search tree. Now, I'm not sure how many of you are aware about this binary search tree data structure, right? But those who are aware, they will be easily able to understand the concept. But those who are not having any awareness about this concept, let me give you again a brief overview of the same. BST says that if, let's say, you want to add any of the element in a tree, you want to create any tree, right? So how the creation will happen, that every element, for example, let's say you will be having an element, maybe assume 100. So BST says that whatever be the next element you want to store, if let's say the next element is less than 100, the root node, this is something that we call as a root node of a tree. Okay? This is the rule of, you can say, BST. It says that if, let's say, you want to store some element which is smaller than this root node, you will always store in the left side. For example, the new element you can say is, I want to store maybe 70. So it will always be available at the left side of 100. But if on the other hand, you are saying that I want to store the element which is bigger than 100, maybe I want to store the element 120. So at that point of time, that element will always be stored at the right side of 100. So this is something which binary search tree implies. Any element, if the value is less than the root value, so it will always be stored at the left side. If there is any element which is bigger than the root value, it will always be there in the right side. So I can say this is the simplest rule ever that we have with respect to BST. For example, in future, let's say we will be having 50. So first of all, I'll try to check the root element. 100 is there, 50 is smaller than 100, so it will go towards the left side. 70 is there, okay. The value of 50 is smaller than 70, so it will go again towards the left side and will be able to store 50 here. If let's say now 90 is coming up, so again always remember in the binary search tree, we will always start from the root node, and definitely whenever we want to insert some new data, it will always be available at the leaf node. For example, you are saying I want to store maybe 90, so what will happen is, it will check, okay, 90 value is less than 100. So it will go towards the left side, because this is the rule which I was talking about. Any element, if it is smaller, it will always go towards left side, and any element which is bigger, it will always go towards the right side. So now it will again compare with the next particular node. By the way, this node is called as internal node, okay? Because this is a part of internal tree, right? And any node whose further child is not available. For example, for this 100, 70 and 120 is a child. But if I'll ask you what is the child of 50, there is no as a child available as of now. So this kind of node in a tree data structure is called as a leaf node, okay? So now coming back to the same discussion, 90 is again compared to the next particular internal node. And now I get to know that, okay, 70 is somehow smaller, 90 is bigger than 70. In that case, definitely it will go towards the right side of 70 and 90 will be stored here. So in this particular case, what we have observed is, this is how basically the data will be stored in a binary search tree data structure. Now, definitely, if let's say you're talking about KD tree, it is built on this BST only. KD means k-dimensional tree. Like k means the number of dimensions which you are really looking forward. Now, what will happen is, it says that let's say you will be having number of data points available with you, and you want to apply a KNN specific algorithm, right? Now you know that in KNN, everything is based upon the distance matrix, and we have to choose the any particular point available in my complete data points, right? In order to examine that what is the nearest one. So how this KD tree is an optimization of KNN, let me give you a very simple example. For example, let's say we will be having a few random data points available with us. Maybe those points are 1, 2, those points are 2, 3, 2, 4, 3, 6, 4, 2, then we have let's say 5, 7, then we have let's say 6, 8, then we have let's say 7, 5, then we have let's say 8, 5, then we have let's say 3, 1, and at the very end let's say we will be having 9, 3. So in a way, can I say that we will be having 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. In a way, can we say that in total we will be having 11 data points, and every particular data point has its own x-axis and y-axis available with us? Now what we will do is, we will try to build a KD tree here. So what will happen is, we will try to first of all check what is the middle value available in this particular entire x-axis. So you can see in our x-axis, we will be having 1, then 2, then 2, then 3, then 4, then 5, then 6, then 7, then 8, then I think again 3 is there. Let's assume that it is again 9, so that it will look in a sorted manner only. 9 and 9. So what is the middle value available with us? So if I'll just try to differentiate between this x and y. So in x-axis, we just have 1, then we have 2, in the next value we have 2, 3, 4, 5, 6, 7, then we have 8, right? Then we have 9, then we have 9. So in this specific case, you will be easily able to observe that what is the median value? How basically we will be able to evaluate the median? We first of all have to sort our data points, and after that we will be able to find the middle value. So here you can see 1, 2, 3, 4, 5 values on the left, 5 values on the right. So it clearly indicates that this is our middle point. It means I can choose this as my root node in the KD tree. So now what will happen is, I will be having 5, 7 available with me on the root part. Now let's start exploring again the further values. It means that the values which are less than 5 will be available towards the right side. It clearly indicates that all these values will be available towards the left side, because it's a part of a BST only. So I want to signify here that 1, 2 followed by 2, 3 followed by 2, 4 followed by 3, 6 followed by 4, 2 is solely available towards the left side of a node. Similarly, if I'll say that on the right side, how many number of points do we have? So here you will be clearly able to observe all the values where the value is bigger than 5 is at the right side, because as per the property of a BST, you can say. So what will happen is, towards the right side, you will be able to observe you are having values like 6, 8. You will be having values like 7, 5. You will be having values like 8, 5, right? 9, 1. And at the end, you will be having 9, 3. Makes sense? So this is how basically our complete architecture looks like. Now, same thing we will do it again. We will try to find out the median again, which is again maybe this for the left side and this for the right side. And again, we will try to split our data points into further two components. And this is how things will be going on until or unless we will be left with the only single point available at the left and the right. Now, the question is, you can ask me, Priya, why we are doing so. So what will happen at the very end, you will be able to observe that you will be left with something like this. You will be having 5, 7 on the root. Then you will be having, let's say, 2, 4. Then on the left side, you will be having 1, 2. You will be having 2, 3, which you will further split again. You will be having 2, 3 and then 1, 2. This is how it will looks like. So now you can observe every value is less than the root node value, right? And on the right side, you will be able to observe 2, 4 is there. Then we will be having 3, 6 and 4, 2 available towards the right side of 2, 4. And again, if you will do the split, you will be able to observe, let's say you will be having 3, 6 here. And then you will be having 4, 2 available here. Similarly, again, if I'll do the split on this right side, you will be having 8, 5. On the left side, you will be having, you will be able to observe 6, 8 and 7, 5 will be there. Then maybe you will be having 7, 5 available with you. And at the very end, you will be having 6, 8 available with you. On the right side, same flow will go. You will be having 9, 1 and then you will be having 9, 3 because on the y-axis, 3 is somehow bigger value. Now, with this creation, this is something which we call as a KD tree, which is built on the BST part, right? It's a binary search tree only, but it's just that we're trying to develop that with a two-dimensional tree, right? Now, in this case, if you will clearly examine, if let's say I'm looking for a data point, which is let's say 3, 6. So what will happen is how basically this particular tree will be able to optimize my brute force approach of KNN. It will simply say, let's say I want to look for the nearest point of this 5, 7. So if you will be able to observe this 3, 6, first of all, first near points are maybe 2, 4 and 8, 5, right? Let's say I'm looking for 3, 6. So I am pretty sure that 3 value is somehow smaller than 5. So it will always be available at my left side. So definitely my huge search on the right side will not be there, right? It will completely be avoided. So this is the advantage of this binary search tree. Those who are already aware about BST, that's the major reason. For searching purpose, only this tree is very famous, right? So in the worst case scenario, its complexity is linear, but in the best case, it can go to logarithmic, right? I'll not deep dive more into DSA part of the same, but definitely it requires the knowledge of DSA. That's why DSA is very much important in order to understand the concepts of machine learning, deep learning. Somehow you will see that whenever we are talking about the time and the space complexity, whenever we are talking about the data structures and algorithms that we have, we will always use this kind of knowledge only. Okay, I hope it makes sense. Now, this is the first optimization of this KNN, which is basically helping me to get that searching of the data points very easily by reducing my search space. If let's say, as I told you, we want to explore 3, 6, we know that it is always available towards the left side as per the property of a BST. So we never ever go towards the right side. So somehow almost half of the search space is reduced here. That is the first thing. Second important optimization is the bowl tree, which I told you, right? This is a second optimization which researchers have done. In this particular case, what they have done is they have said that similar to, so let me just open the documentation. It's not a documentation, but it's just a Jupyter notebook which I'm using here. So it is similar to KD tree. Bowl trees are also hierarchical data structure. What is the meaning of hierarchical? It means tree-based, non-linear based data structures. Now, these are very efficiently, especially in case of higher dimensions. What they want to say, by default, 2 clusters will be created initially. All data points must belong to at least one of the cluster. So let's say you can clearly see, let me open my Epic pen here, right? So what you can observe here in this specific scenario, what we are trying to do is we are trying to create, with respect to this level 1, we are definitely trying to create 2 clusters. This is cluster number 1, this is cluster number 2, and you will be able to observe that whatever data points we have, all those data points will be available in these two clusters specifically. Now what will happen is, distance of the point is calculated from the centroid of each cluster. In the upcoming session, we will talk about something called as k-means clustering algorithm. It is a part of an unsupervised, I would say, machine learning algorithm. So whatever be the mathematical intuition I will talk about in a great detail in this specific algorithm of k-means, you will observe it is somehow similar. The only difference is, when we are talking about this k-means, usually people get confused between these wordings also. It looks same, k-means and KNN, but KNN is specifically designed to solve a supervised task. Means whenever you're applying a KNN algorithm, target column is available to us. In k-means, target column will not be there. That's why it's a part of a clustering technique. It's a part of an unsupervised technique. But how that similar knowledge is helpful in the ball tree, it is also trying to create or find a distance of the centroid, whichever distance is minimum. Again, it can be Euclidean, it can be Manhattan, and if it's a categorical data, it can be Hamming as well. So centroid closure values will belongs to one cluster, another centroid closure values will belong to another cluster. Now what will happen is, again, each cluster is then subdivided into subclusters again, you can see below, right? And then the points are classified into each cluster on the basis of the distance from centroid. This is how the clusters are kept to be divided till a certain depth. So you can see in this diagram how we have a single cluster where all data points will be there. Then we will be having two clusters in which almost all data points will be there, but there is some sort of overlapping you can observe here. After that, again, further subdivision of clusters happen depending upon the centroid's value, whichever find it very close, that is the separate cluster that we have. And again, you can see in the level 4, further subclustering happens. So it's kind of it's a ball tree. So ball tree initially takes a lot of time, but once you will be able to observe that nested clusters are created, finding nearest neighbors is very, very easier. Why? Because let's say I am looking for this specific cluster. Now if I'm looking for some data point, I know that the nearest points will definitely be available in this cluster itself. Why will I jump towards this cluster? Why will I jump towards another cluster? So basically what is happening here, we will be having one bigger cluster, one bigger ball, you can say, depending upon that centroid value. What is the meaning of centroid? Centroid means the middle center, which is basically we can evaluate by taking the average of x's of all the points and y axis of all the points. Okay? Anyhow, if this conversation seems difficult to you, you can just skip that portion, because in k-means I will show you the practical illustration of everything with the numerical example. So what we are trying to do, we are trying to just split our clusters in a depth so that we will be able to differentiate all the clusters. And now what will happen is, we know that in a cluster we have all the nearest points. So if let's say I'm looking for the nearest point for this part, I know this is the nearest point because this is available within that cluster. So this is another optimization I would suggest that we have in case of a KNN algorithm. So we have two further optimizations as we have discussed. One optimization is a part of, you can say, KD tree. Another one is a part of a ball tree. And both of them is basically helping me to reach to a point where I will be having multiple, I would say, nearest points available with me, and I will be easily able to find out the nearest clusters very, very easily. So ball tree is having an idea that we will try to create one cluster initially where we will be having all the data points. Then we will keep on splitting our clusters into multiple components until our all clusters will be separated, with the hope that, let's say, if in future you will be having these clusters and you want to find the nearest point of, let's say, this particular point, you know that these are the nearest because this belongs to within one cluster. So it again makes it very, very easy to find the nearest neighbors in a given algorithm. That's why if you will again go back and refer the documentation of KNN algorithm, you can say sklearn documentation, if you will just search that particular stuff, you will be able to see that in this particular algorithm, when you're talking about algorithm, it gives us multiple kind of ways: auto, ball underscore tree, KD tree, and root. By default, it is auto. So ball tree will use that ball tree algorithm where I have talked about the clusters thing. KD tree will talk about a BST approach. Brute force is a brute force approach that we have discussed in the very first video. Auto will attempt to decide the most appropriate algorithm based on the values. So depending upon what kind of data you are dealing with, if you're passing this auto keyword, it will automatically decide, depending upon what kind of data you have, that which particular algorithm might fit in. It might be a ball tree, it might be a KD tree, it might be a brute force approach. Now, the good thing is, I believe that you should not, apply any specific approach, because in terms of optimization, okay, these are good values, but it might be the case that there will be lot many computations which will happen internally. So it would be great that if we will just mention this auto keyword, which is by default, so that there is no need to specify also algorithmically. So what will happen is, depending upon what kind of data you are dealing with, it will automatically take the parameters and fill up that values. So now I hope that you will be able to get a clear-cut idea about the optimization of KNN, how KD tree works, what's the internal intuition behind that. Afterwards, we have explored towards the ball tree, internal intuition behind that as well, and how basically these two algorithms helping the model in order to optimize it further, to get the nearest distance in a easily optimized manner. With this, let's end today's video. I will see you all in the upcoming video, where now we will talk about the implementation of KNN algorithm. Whatever concepts we have explored so far, right? We will try to use those concepts in terms of implementation. Also, if you remember, we have done one project of predictive analysis in healthcare domain when we are talking about a logistic regression model. So what I will do is, I will try to use that same collab file, and on top of that itself, we will try to apply the KNN to solve the classification problem. I will let you know that if, let's say, the same problem, if you want to apply the similar algorithm, but for the regression per se, which algorithm you have to use and how basically you can implement that as well in the upcoming part of the video. So in a way, I will try to show you both of them, how you can apply the classifier and the regressor, both of them in the upcoming stage. So just make sure when you will, went towards the upcoming part of the video, just open that previous file of predictive analysis of healthcare domain. That would be of great help. And whatever things I am doing, please try to do the similar steps in the, in your own collab file, so that you will be able to understand in a very great manner that how basically the implementation will be done. So with this, let's end today's video. I will see you all in the upcoming video, where now in the very last part of the section, we will discuss the implementation of this algorithm. Bye bye everyone. Stay tuned.